Just begin. Our speaker, Setsuro Fujiie, Microlocal method for the semiclassical distribution of quantum resonance.
Thank you for the introduction. And I'm very happy to have a chance to talk to you in this very beautiful town. And I thank very much Korea for organizing for the meeting. And I do my introduction on the blackboard. I have to explain semiclassical analysis and also quantum resonances and microlocal method. Okay. I begin with the well-known orthogonal conservation condition for the one-dimensional Schrödinger equation. So first, before that, I have to explain what is semiclassical analysis. So if I write capital P, this is minus Laplacian plus dx. That was taught by many other speakers, but I put here x squared coming from the Planck constant square over 2m, m is a mass. But I write h and I regard it as small parameter, not constant. So it is very small. And for this operator, I consider the stationary Schrödinger equation. And for this equation, I consider the eigenvalues or the subject of today's talk is resonances. And it is remark that all these quantities, eigenvalues or resonances, depend always on h. And the purpose is to know the asymptotic distribution of eigenvalues or resonances. And I compare this result with the underlying classical mechanics, which is described by the classical Hamiltonian, which I write with small p, which is a function of x and xi. So x is in the Euclidean n-dimensional Euclidean space, and c also, which is momentum, which is defined by c squared plus d of x, which is obtained by replacing h over I partial derivative differentiation with respect to xj by psi j. Okay. And on this side, I consider the Hamiltonian system, which is ordinary differential equation. So for the point in the fixed space t psi t, which should follow the equation, the Hamiltonian equation, which is dp dxi, which in this case is exactly 2 psi, and c dot t is equal to the derivative minus dp dx, which is in this case dv dx. Okay. And when I solve this equation with initial value at equals 0, given at x0, x not 0, I will write the solution xt dt, xt xi t as x. This is just a notation. So the famous Bohr's correspondence principle says that in the semiclassical limit h goes to 0, we should find classical quantities in the quantum mechanics. So the purpose is to rigorously justify this assertion. And today's talk concerns the asymptotic distribution of resonances and the trapped set of the Hamiltonian system. I explain this by beginning by the well-known Bohr-Sommerfeld quantization condition. So the dimension n is 1. So example. Okay? Let us consider a potential of such form, shape, which we often call simple wave. And let us look for eigenvalues near such energy E0, such that you have a wave here. So there are alpha E and beta E, which depends on E, such that outside this interval, it is forbidden for classical particles to enter, and here classically allowed. In such case, it is known that as Bohr-Sommerfeld quantization condition. So I write rules, okay, which say that if E, energy E, is an eigenvalue, then it should satisfy the equation A E is equal to 2k plus 1 pi h. Now, I should be more precise. E, eigenvalues near E0 should be close to the root of this equation. But in which sense close? It should be rigorously justified, but I don't mention that for the moment. And A of E is actual integral. This is equal to alpha E to beta E of square root E minus B of X dx. And for example, in the case of harmonic oscillator, where the potential is exactly x squared, then this can be exactly computed. And as you know, this is in this case, A of E is equal to pi E. Simple calculation.
So your AE is an Agnon distance, or
yes, Algol distance is used. The terminology Algol distance is used to express something like that, but usually D minus E in the below potential. But anyway, it's something like that. So if you put pi E here, you have E is equal to 2k plus 1 H. It is exactly the eigenvalues of the harmonic oscillator that you know well. Okay? But this is always true for any simple wave potential. That is the assertion or quantization condition. Okay? And this classical, this classical adaptation can be written in this form also. If I draw the picture of the Hamiltonian system of such situation, then in the phase space, in a one-dimensional case, it is easy to draw the picture of the flow because of the dimension, the special dimension. And it should be like something like that. Okay. And if I call this closed trajectory gamma E, then this quantity can be written in by line integral. Okay. So anyway, distribution of eigenvalues is a quantum-side quantity, but it is described at least at the principal level by using classical quantity. This is one thing which explains correspondence principle. And I want to explain more things using this example, that is microlocal method. In a very intuitive way, it can be interpreted as follows. So, yes. Classical mechanics describes the motion of particle, but it is well known that in the quantum mechanics, it has a property of wave. In fact, the solution eigenfunction should have a form like that. U, which depends on h, is some amplitude times exponential I phi x over h. So it has the form of wave. Okay. So very intuitively, if it is a wave, then you should follow along this curve, which should be the principal part of the wave. And here, the phase should coincide. This gives exactly the Zomov condensation rule, which discretizes the energies. This is an intuitive interpretation, and we will justify this intuitive picture using the Microlocal method. Microlocal means to study functions of x, not in the space of x, but in the space. At point of x and x and z. This is the Microlocal method. Okay. Okay, so I continue. So I continue with this expression. Then, if I continue this form along this gamma, but it is well known by Maslow's theory that I can express the same U after one round tour here as also in the WKB form. So it should be some another amplitude and another phase. Okay, and the new phase, a new amplitude can be expressed in terms of the old phase and old amplitude. How? The new phase should be the old phase plus action. This is exactly this, A of E, plus some phase shift, which is called by Maslow's index. In this case, it's minus pi I. And in this one-dimensional particular case, the phase doesn't change. At the principal level, that is, if I develop this amplitude in the power series expansion, asymptotic expansion, then the first leading term doesn't change. This is the leading term, is the same as the old one. Okay? Then, at least at the principal level, this identity shows that, so this is A0, and this is different. So this gives that exponential I, so C dx minus I, so I should remove I here, minus pi h over h, so over h should be equal to 1. Okay? the multiplicative factor that you obtain after one round tour is this quantity. And in order that the two solutions coincide, this should be 1. And this is equivalent to the Bohr-Sommerfeld composition condition. This means this. This is the intuitive interpretation of the Bohr-Sommerfeld composition. And so, next, I would like to explain resonances. Okay. So now we saw that the main thing that produced eigenvalue is only this part of a potential. Okay. The behavior of the potential outside this well doesn't affect the distribution of resonance. Then, natural question is to consider potential which is modified outside the well, like that. So here, exactly the same as that, but outside, I modify the potential so that it decays, or more simply, to have a compact support. Okay. But as you know, such potential has no positive eigenvalue. Okay? It's a scattering plot, so you have no eigenvalue. Because in the one-dimensional case, it's very easy to prove because any solution outside the support of D is explicitly given like that. Okay? And in order that such function to be in L2 space, C1 and C2 should be 0. That is, there's no non-trivial solution in L2 for the equation T is okay? So then, Bohr-Sommerfeld condensation condition has no meaning. Yes. So even in this case, it has meaning in the following sense. If we so it has resonances which is approximated by Bohr-Sommerfeld condensation condition. What is resonance? Briefly, I don't define in the general case, but E is a resonance when there exists non-trivial U such that the problem PU is equal to EU, like the eigenvalue problem. But here, instead of U, the fact that U is in L2, I impose another condition which is outgoing, which means that U is equal to, in this compact support case, is that for very large x, it is of the form H, and for x very negative, it is some here you have minus. So physically, this one with plus sign is considered to be a way to right-going way, and minus one is left-going one. So this means that on the right it is right-going, on the left it is left-going, so it's outgoing solution. Okay, and this is not very practical, useful to define resonances when one wants to generalize to the multidimensional case. But if you look at this solution, for example, for complex x, but so in the with some small angle theta, if you look at this solution, on this line, this solution is L2 because it decays exponentially fast at infinity. So this resonance problem can be seen as eigenvalue problem also for a modified operator at infinity. So, E is eigenvalue of the operator P theta, which is defined by sandwich with U theta P, where U theta is, if it is, it is operated to a function f, it is by definition f ei theta x. So, of course, this P theta can be written in this form, minus is h squared Laplacian plus exponential I theta d ei theta x, something like that. So this is no longer self-adjoint, even though d is yes.
Sorry, when you have completely supported potential, when you apply this deformation technique, you need analyticity by
yes, you're right. Exactly. So yes. So it is impossible because of the non-analyticity of the potential. I cannot dilate on the whole line. So I should dilate. In fact, so it's a good remark that I skip. Yes. In fact, I have to take such line instead of such line. Some curve which stays on the real, and after the support, it goes there. Okay. But it doesn't change the definition. Yes. Yes. Distortion, something like that.
But just in that case, on your exponential factor, you have some characteristic function supported outside the supporter.
Characteristic function is not. Yes.
This is exponential minus 2i
Theta
yes. Times 1 on the exterior of the support of
yes, yes. Thank you. Anyway, this changes the form. But what is important is that because of this dilation or that distortion, this is no longer self-adjoint. So the resonance are not real; they are complex. And if you see by the Y theorem, okay, this is because of the compact support. This is Laplacian compact, so it doesn't change the essential spectrum of this minus Laplacian, which is the half line positive d-axis. But you multiply with this, so the essential spectrum of P theta becomes something like that here. This is the essential spectrum of the modified operator P theta. And thanks to this, we open the place for which we can continue the resolvent. And you may find some poles of the resolvent there, and this coincides with the eigenvalues of P. So these poles of the meromorphic continuation of the resolvent are called resonance. But in the one-dimensional cases, the first definition is much easier to understand, but it is not easy to apply. So resonances can be defined also by as the pores of the scattering matrix and so on, but it is complicated and I don't talk about that. And okay.
It seems like the condition. I mean, the last way of phrasing it depends on theta.
Yes. It's also very important. So, as the distinction depends on theta, so it may depend on theta, but in the following sense, it is independent of theta. So, if I denote this angular domain by phi theta, this is this domain, then the resonance in this domain is equal to another phi theta. Of course, this should depend on. Okay. Sorry. For theta smaller than theta dash prime, then the resonance defined by theta and resonance defined by theta prime coincide when restricted in the smaller domain. This is, in this sense, it is independent. Okay. So, as I said, resonances are complex and in the lower half plane, and especially when we study the semiclassical analysis of resonances, the imaginary part of resonances is very important because if you consider the evolution operator, which is written, evolution operator is minus I T P over H. This is the evolution operator, the Schrödinger operator. And if at least formally, if I replace this P by the resonance E, then we have this complex number. But the absolute value of this number is equal to exponential minus T over H. So, different from the eigenvalue problem, in the state, quantum state corresponding to a resonance is decaying. And the imaginary part of E expresses exactly the rate of decay. But the inverse is so it is the lifetime of the corresponding resonance state. So physically, it's important to find resonances closer to the real axis because it has long lifetime. Now, so as I said, even though the resonances are on the lower half plane complex, but they are very close in this situation. They are found very close to the real values which satisfies the Bohr-Zumwalt conservation condition. I will state this as several later more precisely in the multidimensional case. So I start the slide, I think. Okay. So the general question is the following. Is the relationship of the following two things. On one hand, the quantum side, we look for the E0. We fix positive energy fix. On one hand, we study the asymptotic distribution of resonances. May I use different colors? Resonance in a complex neighborhood. Is it visible? No.
On the,
No.
on the second row, it's okay. But
Maybe. Is it okay? No. No. In a complex neighborhood, small neighborhood is a neighborhood of E0. Well, in the complex plane of the energy, we fix some positive E0 and we fix some small neighborhood of E0, complex neighborhood, and we look for the resonances and the asymptotic distribution on one hand, and this, and on the other hand, the trapped the geometry of the trapped set of the classical on the classical mechanics. That is mechanics. That is that I denote K of P0, which is the set in the point in the phase space where the value of P, small p, is E0, such that the flow, Hamiltonian flow, starting from this point, xi, does not go to infinity, both as t goes to transport minus infinity. Okay? Do you?
goes to infinity.
No, sir. Yes. Thank you. Okay. So, of course, in the let us take an example of multi-dimensional case, but I write a one-dimensional picture of two bands like that, like the previous one. So let us take an example of two bands. One is big and one is small. Okay, this is the picture of P. Then, in the phase space, this is this. For example, if you take an energy E0 here, for example, at this level, then the classical trajectory is something like that. Particle comes here, goes, and here also something like that. Okay. The critical point, for example, if E0 is here, then it should be something like that. And here, if it is at this level, then it is something like and if you are lower than this, such level, then you have a closed periodic trajectory, as I explained in the introduction. Okay, so for example, if, okay, so I start this slide. So I prepare some notation. If I write both E0, C1, C2, this is a neighborhood of E0 in the complex plane. With center E0 and rectangle like that, where this is C1 and this is C2. Okay? And when sometimes I will say that the set in the complex plane A and the set B are close with distance delta, but when one is restricted in C, in the following sense. So if you take any point A from this set, but in this set also, then you can find some B in this set, such as that, and vice versa, in this set. So if I say with this definition, if I say like that A and B are close, then unfortunately I don't state anything about the one-to-one correspondence. But we will use this such notion. Then I start with the case where there is no trapped trajectory. Okay. So, for example, if E0 is such level, then your trajectory is like that and like that. So like, which means that any point on this set goes to plus infinity as time goes to plus infinity and also minus infinity. Okay? So there is no point trapped permanently in the compact set. So this is no trapping energy. And very basic result, no result is that if you look for resonances in such box rectangle with epsilon for real part, and this for any C, h log h for the imaginary part, then you don't find any resonance if E0 is a non-trapping energy. In this sense, trapped set is very closely related with the existence of the resonance close to fixed energy. This is the first starting point. I wrote two names, but first one is on the assumption of the analyticity of the potential. The second one is on the assumption of only C infinity. And slightly, the result is different, but I wrote, this is the result of mathematics. And second one is when is this part. When the trap set consists of a single periodic trajectory, just once periodic trajectory. Then, so I write here so a picture. So say this is E1 and this is E2, this is level. Then below E1 you have, roughly speaking, such quantization rule which is similar to Bohr-Sommerfeld quantization rule if you forget this one. Okay? Action integral around the trajectory is equal to some integral multiplication of phi h. But the difference is here. You have imaginary part. And in fact, if you look at this, very roughly speaking, you have a lattice structure horizontal. And especially the neighboring, the imaginary part of the first line is of order h. And the neighboring distance is also of order h. Very well. This is this result. And if I explain very briefly this result, then from the Microlocal picture, it can be interpreted like that. So you begin with some WKB form expression at one point, and you do round trip, and you come back here. Then the one-dimensional case. Okay, so you have also such form, and in the one-dimensional case, just phi tilde is phi plus action plus something. And I said that in the one-dimensional case, the principal level of A tilde is equal to A. But in the multidimensional case, you can imagine that you have two bands. Okay? Between two bands, you have only one trajectory where you can go and back. But once you move a little bit, then you should go to the infinity, very easy. So the amplitude of the WKB solution should decrease while traveling. That's why A tilde is smaller than A. And the condensation condition, very roughly speaking, is some rho of E, some function E, and action is equal to 1. In the one-dimensional case, it will equal to 1, and in this case, rho is some function of E whose absolute value is smaller than 1. And if you solve this, then you solve it, but you freeze it in E0. Then, of course, E should be imaginary, because if you take the imaginary part, absolute value, this is smaller than 1, and this is 1 if E is real. So it cannot be 1. To compensate, say this, E should go down to the complex lower plane. And if this is independent of H, then the imaginary part is of order H. It is easy to check. Yes.
Your amplitudes, are they assumed to be positive and non-negative functions? Or
But
your amplitude functions, are they non-negative? Or
this is complex.
is it complex?
It's complex. Yes.
So there is some not completely well defined how you separate into the phase and the amplitude.
I know, how to separate the, yes, of course, without saying, I suppose that A of x psi has some asymptotic span of the form yes.
But you don't assume
But
that
this one doesn't have such asymptotic span. So in this sense, you can separate.
Ah, I see.
Okay. So next, yes, hyperbolic fixed point problem is that if we are here, then classical particle, which comes, for example, from the left, with this E2 energy, will take infinite time to reach this maximum. In this sense, or if the particle here doesn't move at all. So this point is a trap set, belongs to the trap set. And if this is the global maximum, then this is the only trapped point in the K0. Okay? So in this situation, I should explain. So the situation from this fixed point is that something like that. If I suppose that it is the origin, so there is two stable manifold, which is obtained by stable manifold theorem. That this one I call lambda plus, and this one lambda minus. And lambda plus is by definition the point of x psi such that the flow from this point converges to the fixed point 0 as this is so t minus infinity. Okay. And of course, lambda minus is vice versa, like that. So, okay, when t goes to plus infinity, it goes to the fixed point. And it is known that lambda plus and lambda minus are n-dimensional Lagrangian manifold. Okay? And in such a case, resonances are like that. If let gamma lambda be such discrete set defined by lambda j is something like the curvature of the maximum, the Gaussian maximum. And this is in fact, this set is in fact the set of eigenvalues of the multidimensional harmonic oscillator. The harmonic eigenvalue of this operator is exactly this gamma lambda. Then resonance is close to resonance 0p, approximate resonances, which is E0 minus IH gamma lambda. That means that they distribute close to E2 like that. Okay? This is a sequence of eigenvalues of harmonic oscillator, but in this direction. And this can be seen intuitively because this Maybe I don't have time, so I skip this explanation. So it remains the problem near E1. How is a trapped set at E1? It is exactly, you have a hyperbolic fixed point here, and also a trajectory like that, which goes to this fixed point as t goes to minus infinity, and also t goes to plus infinity. And such trajectory are called homoclinic. Okay. And in such case, we have such condensation condition, which is in a sense similar to the Bohr condensation condition if you don't have this. Okay. Exponential, okay, this is some change of symbol amplitude, but in addition, in such homoclinic case, you have this one, h to the power something, which depends on e. Why? Because at the fixed point, if the quantum wave come outside to the fixed point, after that it scatters at any direction. So you lose much weight. After that, at the exit, your amplitude is much smaller than before. And this is expressed with this power of h. Okay? It's very intuitive explanation. And this, because of this, the structure of the asymptotic distribution is quite different from this hyperbolic fixed point case and hyperbolic closed periodic case. And it is, if we look for only the first line, it is like something like so. Something like that. And you have only to solve this equation. But I say that here the imaginary part is some d0 minus d0h. So minus d0h. Imaginary part is d0h. So h micro of a d0, where d0 is the sum of lambda j of j equal 2 to n. Lambda j are the curvature of each direction, and they are ordered in the increasing order. So lambda 1 is the smallest curvature, and lambda 2 is the second smallest curvature. The sum of this is d0, and it is the imaginary part is defined by determined by d0. And also the distance of neighboring two resonances becomes, instead of h in this case, log h. So condensation resonances in such case. And I have only 3 minutes.
Sorry.
Yes.
In this original case, to the left you have sort of a lattice.
Hmm?
To the left you have several rows of
Yes.
resonances, and it transitions into just having one curve.
No, I restrict myself to a smaller.
Sorry.
Yes, because I don't know what happens there. You know. Anyway, the first line is the most important, but okay. The second line is difficult to analyze. Yes. Okay, so in order to justify such intuitive explanation, I use Microlocal method. Okay, this is a formula when I solve the condensation condition for the homoclinic orbit. Okay. So you have for the real part, the distance of neighboring two resonances is of h log h, and for the imaginary part, the dominating term is d0h. So, just I would like to talk just a bit of microlocal method. So you can forget resonances now. And first, I want to explain how to analyze a function of x only in the phase space where x and c. So given a u of x, which depends on h, parameter h, that I suppose L2, and I normalize like that, then, and let rho 0 is a point in the phase space, then we say that u is microlocally 0 near some point in the phase space when I localize u with phi. Phi is a cutoff function near x0, and I do the Fourier transform to go to the c function, and there I cut off with phi, which localize near xi0. So at the same time, I localize in x and in xi, and I measure this function with L2 norm. And if it is very small, h infinity, when h goes to 0, then we say that this u is microlocal 0 at this point, near this point. Okay? And the set of xi, the complement of such point is called semiclassical wavefront set, but I don't use this terminology. I use always this microlocal 0. Okay, there are some important examples, but I skip, and I consider the case where our function u is a solution to some differential equation, but for us it is enough to consider Schrödinger equation. Okay, so from now on, u is a solution to the Schrödinger equation, which is in L2. Okay? Then first thing, very basic thing is that if the classical Hamiltonian, it doesn't vanish at the point rho 0, then the solution is automatically 0, microlocal 0 at this point. This condition is often called ellipticity, microlocal ellipticity of p at point p0. So at the elliptic point, u is always 0, microlocal 0. The second one, by Hermander, is the most important in the microlocal analysis, is that if, so now, rho 0 is supposed to be a point where p, the value of p is 0, because if it is not 0, it is elliptic and u is 0. Then, what we can know is that if u is microlocal 0 at one point like that, then u is always also 0 at any point on the Hamilton curve starting from this point. Okay, this is called the so-called propagation of singularity. This is the basic fact of the microlocal analysis. And when we are concerned with such hypothetical fixed point, we need also such theorem of propagation of singularity. The problem is that if u is 0 at some point, is it possible to say that it is 0 also here? Herman's theorem says nothing because the Hamiltonian flow cannot go through the fixed point. It stops before the fixed point. The answer is that if u is microlocal 0 at any point of lambda minus infinite stable manifold, except at the fixed point, then you can conclude that it is also microlocal 0 at any point on the stable manifold. I won't say stable manifold. So in order to if so, it says that if it is 0 here and also it is 0 here, then you can conclude that it is also 0 here and 0. You need more information. Of course, you need all the information for the incoming waves in order to know the information of the outgoing wave. But one thing is important is that except some energies, this is exactly the resonance set created by a hyperbolic fixed point. So you should avoid such energies, then you can conclude such theorem. Okay, so it was the microlocal propagation of singularity, but now I would like to be more precise. Let us consider such problem that we call microlocal Cauchy problem. That is, we are given a set, a region, omega, in the phase space. And we suppose that this equation is satisfied at least in the microlocal sense. And given two open sets, omega 0 and omega 1. And suppose we are given a Cauchy data, U0, but microlocally at omega 0, which means that the difference between your solution U and the Cauchy data U0 is microlocal 0 in this small domain. And the question is that, then, is this data determines U in the microlocal sense at another domain omega 1? Is it unique? And second question is that, if it is unique, is it possible to express U microlocal in omega 1 using the Cauchy data U0? Okay. And the answer is in the next page. The first one is a result by Maslov. And first, the solution is, yes, so now we consider the case where, so you have a point rho 0, and you have a Hamilton flow. Okay. You take another point rho 1 on the Hamilton flow. And as omega, capital omega, I take a neighborhood of the whole flow, and as omega 0, I take small neighborhood of rho 0, and omega 1, I take small neighborhood of rho 1. So the first question is that if microlocal data is given here, then microlocal solution here, is it unique? But it is yes, because this assertion is exactly the same as the propagation of singularity. Okay? If it is microlocal 0, if you have two data, different data, if you have data, if it is 0 here and it is 0 here, this is a uniqueness assertion. Okay? So this is uniqueness is exactly propagation of singularity. And the second one is due to Maslov, and which said that if, in particular, the data is of WKB form, I should have written by like that, because in omega 0, which means that this minus this is microlocal 0 in this set. Okay. Then, of course, it is unique But Maslow said that at omega 1 also it is of WKB form. Okay? And the correspondence of the symbol and the phase is given like that, which is exactly that I explained in the introduction. That is, the phase at rho 1 is given by the old phase plus action plus something phase shift, which is called mass of index. And A1, this is important, that it is mass of has explicitly given this constant, but what is important is that if you restrict to the first term of the symbol, then A1 is some constant multiple of A0. You don't differentiate and so on. Just you multiply some constant depending only on this curve, the geometric constant, which is independent of H. So you don't change the order in H, in parts of H. This is very important, right? And a very new, not very, a new result is that concerning the hyperbolic fixed point. Okay, the first one, existence and uniqueness. And uniqueness is also the same thing as the propagation of singularity. So it is true. And in this case also, if U0, the data is given in this form, in WKB form, which is associated to some point here, I decided it. And for example, it is here, 0. Okay. Then, on lambda class, also, it is given by such form. And as I said, the important feature in this case is that it is also in the WKB form, but the symbol is much smaller than this, multiplied by some positive, some complex power of H. This is the feature of this case. So I sketched very briefly, very roughly, how to prove the quantization condition associated to, for example, this homoclinic curve. The first one is that resonance problem or such eigenvalue problem is a global problem. It concerns with the global behavior of the solutions, but it can be reduced to a microlocal problem only near the trap set, because we can have such theorem which says that if U is microlocal 0 just on the trap set, then automatically it is globally very small. And this can be proved using only the propagation singularity of Hermann type. Yes. Because, very roughly speaking, I write, this is general fact, so I write some abstract picture. So, let gamma minus is a set of points in the phase space such that the flow from the point in the set is trapped only in the positive sense. And minus infinity, it is not trapped, but in the positive sense, it is trapped. And gamma plus is contrary, conversely, it is a point of the set trapped at t minus infinity. Okay? Of course, the intersection is our trap set. Okay? And I suppose that this is the set P inverse E0 characteristic set. And we know that if we are not in this set, our solution U is always micrograde 0. It is 0 here, outside this such set. And I have to use another important theorem. The fact is that in the incoming region, where the flow is incoming, the resonance state is micrograde 0. You may, I would like to record that resonance state is outgoing, but it is true also in the microlocal sense. So in the incoming region, it is 0. This is due to the fact that U is resonance state. Then, by the propagation of singularity, it is 0 here. If it is equal to plus infinity, it is 0 there, and it is 0 there. But it is 0 also here. But you can say that it is also 0 in here, because the flow stops before K0. So if you know that U is 0 also on the trap set, if it is 0 also here, then from here you can propagate the singularity, which means that it is 0 also here. So, in conclusion, under this condition, U is everywhere 0 microlocally, and this fact implies that U is small locally, globally in L2. If a function is everywhere 0 microlocally, it is globally 0. This is the first thing. So the problem is just reduced to the trap set, and we have to show somehow that U is of WK form on the trap set. For example, in this case, here U is of such form. Okay. And third one is that using the microlocal Cauchy problem, we continue this solution all around the trap set, and I come back to the original point, and I compare the old one and the new one at the principal level, looking at the principal part of the asymptotic expansion, and of course it should be the same. So then single valuedness of the trap set on the trap set at the principal level of the WK solution gives the condensation condition. Okay, like that we obtain condensation condition, and we define this set resonance 0 approximate resonances. So after that, it remains to prove that the true resonances are close to resonance these approximate resonances which satisfy the condensation condition. For that, I don't go into the detail, but we should only use some elementary contradiction argument to prove that. And first, we show that far from the approximate resonances, there is no resonance, or more precisely, we can get some resolvent estimate which is an estimation from above by some negative power of h. And using this, contrary, we can show that near any approximate resonances, we can find at least one resonance. This is the strategy. So it is exactly the same as my intuitive explanation. Just we use microlocal analysis. And at last, I want to proceed to more general case where you have many pumps. Okay? Till now, we had only 2 pumps, but it's very interesting to consider more than 3 pumps because I should explain something about that. Okay, so let's come back for the moment to the problem of closed periodic trajectory. This result, due to Gerard and Chester that I presented before, was a corollary, in a sense, to the problem of X-ray problem. You consider wave operator or minus Laplacian without any semiclassical parameter, and you consider the scattering problem in the X-ray domain of 2 convex obstacles. This is obstacles, so you consider the equilibrium boundary condition here. Okay? Then the resonances, or maybe people say scattering poles, the same thing, but scattering poles. The distribution of scattering poles at infinity is closely related to the geometric optics, that is, the existence of the trapped set of the geometric optics. This is non-trapping, but if these 2 convex obstacles, the two obstacles are convex, you find only one tracked trajectory here. Okay, and Ikawa studied the asymptotic distribution of resonances for such situation, 2 convex poles. And they found something, and it was a counterexample of the Lattice-Philip conjecture. Lattice-Philip conjecture was a conjecture which asserts that the relation between the trapped set of geometrical optics and the distribution of resonances. So it was very famous, and after that, Gerard and Chester generalized this problem to the Schrödinger problem, like that. But it is very natural to consider, after this example, the example of 3 convex obstacles. Okay? What happens in such case? It should be the same, but not at all. Because if you have more than 2 obstacles, the trapped set becomes very, very complicated, and it is known that the trapped set becomes fractal of fractional dimension. And it is no longer easy to get quantization condition because it is too difficult to follow to continue our asymptotic solution. So it's very difficult. So in a sense, such problem is still very active. And for example, Zworsky, Szczestran, and so on, they studied such problem, and it is often called fractal Y law and so on. But it is difficult to get quantization condition. They estimate the imaginary particle resonances, and so it is successful, but it is the limit. But in our case, in our Schrödinger case, and if we are concerned with hyperbolic fixed point, for example, if you have 3 bands, okay, of course, if you 3 bands of the same height, of course, if you consider an energy below this maximum, then the situation doesn't change. The trap set is very complicated. It's very, very difficult to obtain the quantization condition. But if you consider E0 just at the top, then you have from this, you have only, so in the phase space, you have 3 fixed points, right? And one trajectory starting from this and ending here, and also here. Like that. So you have 6 heteroclinic orbits. And the structure is not at all complicated, not fractal. So it is still possible to follow our strategy to get quantization condition and precise asymptotic resonances. So not only such case, but also in the case where you have many bands, but if the trap set consists of only hyperbolic fixed points, finite number of hyperbolic fixed points, and associated homoclinic or heteroclinic orbits, then our strategy works always. And we can, even though it is complicated, we can obtain quantization condition. Let us see. So let D be the final set of hyperbolic fixed points, and E final set of homoclinic or heteroclinic trajectories associated with these hyperbolic fixed points. Okay, like that. So in this case, you have 3 fixed points and 6 heteroclinic points. So then, in general, this trap set can be, and I suppose this is the most important thing, is the assumption that the trap set consists of only of this fixed point and homoclinic or heteroclinic orbits. Okay. Then such picture can be regarded as a graph. Okay. And I go quickly, but zeta was the power of H that you saw in the quantization condition at the fixed point D. So zeta, we have zeta B for each maximum. And I take Z instead of E as a spectral parameter. It's just the same thing. Okay. Then, for each vertex D, fixed point D, we take this alpha D and D beta quantities, and for any gamma is a path. So, for example, gamma may be this path or this path, and so on. Any path or cycle. You sum up all these quantities, and finally you take the quotient of alpha and beta, and I call this damping index. And for all the sides in the graph, I take the minimum damping, and I call it minimal damping. So sorry, without it. Then for the quantization condition can be given by a matrix whose size is the number of edges. That is number of hyperbolic or homoclinic orbits. So in this three band case, this is a 6 by 6 matrix. Okay, and the element is given like that. That is, so if I have only 2 minutes, so I don't do that, but okay. So when E tilde entry, E and E tilde are edges, and we have to give something when the end point of the starting point of E and end point of E tilde coincide. That is, E tilde and E are connected by some. Then I give something which comes from the Microlocal quotient problem, that is, which gives the multiplication factor from a point on E tilde to a point of E tilde. WKB solution is multiplied by this quantity. And otherwise, it is 0. Okay. Then resonances are close to some set in this sense, where these approximate resonances are defined by this identity matrix minus this big matrix as determinant 0. In other words, the eigenvalues, one of the eigenvalues is equal to 1. Okay, so in the 6 by 6 case, it has 6 eigenvalues. At least one of them is equal to 1. This is the quantization condition. So there is nothing. So in the case of 3 bumps, the matrix becomes like that. Sorry, but there is no sense if I don't. Yes. There are 6 edges, E1, E2, E3, E4, E5, E6. And if I give names like that, sorry, the matrix Q is like that. And if I assume that every bump is isotropic, and if the curvature is all the same, then this factor is in factor, and it can be the quantization condition can be explicitly computable, and we have in fact 6 eigenvalues, but 2 of them are multiplicity 2. So anyway, we have 4 lines for the resonances. This means that this is the real axis, this is E0, sorry, and resonances accumulate along these curves. So you have this is a result explicitly computable for this case. Thank you very much. I stop.
Any questions?
Yes?
So how much of this is multidimensional?
Sorry, how much?
So yeah, the pictures are all one-dimensional, so it's sometimes I lost track of which results are in higher dimension, which
higher dimension. Everything
this is certainly
yes.
higher dimension.
Yes.
So did your bumps, are they rotational in invariant?
What is rotation?
I mean, your bumps, are they?
Bumps, yes.
The level curves, are they circles? Like you draw them, or?
I guess this isotropic meant that they were
Yeah.
gravity, from which side?
So the level sets are
Level set you mean P inverse E0
for the bumps.
for the bumps, yes.
You drew the bumps as if the level sets of the bumps are disks.
Yeah. This when E is below the maximum, yes, of course the level set is like that. But I don't consider such difficult problem. I consider only the near the resonances near the maximum.
Sure.
So it is 3 points. Just 3 points.
And all the bumps look the same and rotation invariant.
No, it is just a particular example. I said that only for example. So the theory can work for any case.
Yeah.
So for the potential, your assumption is just analyticity.
No, C0 infinity.
C0.
I don't assume any analyticity. This is one thing which is new in this domain. Yes.
And in any part of your analysis, you use escape functions and instruments. I mean,
Escape function, yes. Some of the result that I presented, they use escape function, but for my result, I don't use escape function.
yeah.
For the non-trapping case, you can construct escape function to show the non-existence of the resonances.
That's good. Yeah.
We study resonances, so I don't.
Okay.
Yes.
And what do you think about the case where you have periodic structure plus potential which you can see? Even from
Periodic potential, you mean?
yeah, a periodic potential plus some sort of you consider the resonances for the periodic crystals that you can try. You have a periodic structure.
Yes,
and
I thought that it is possible with our strategy, but I think that if you have many bands periodically, then you have other trajectory other than that, such homoclinical that is the structure, the assumption that the Tropsch set consists of only hyperbolic fixed point or homoclinical heteroclinical orbits is not satisfied, I think. They are particles with energy E0, but which doesn't pass the maximum.
yeah.
So our solution U exists everywhere, and the problem becomes.
Yeah,
But I don't know.
But it has a physical sense, yes?
Yes.
It has to be some sort of very natural.
Natural, yes. So, yes.
More questions?
Maybe this is a stupid question, but what if your bumps were delta functions? Could you,
Yes.
could you
Anyway, our strategy doesn't work in such thing. But maybe I know someone.
Okay, you
but
compute.
maybe you can compute things explicitly.
Compute explicitly. Yeah.
Your bumps are delta.
Yes. In such case, I think there are some results because in such case there's no such difficult problem. Yes, in a sense it's the same. In the case of the presence of magnetic field, there's someone whose name is Tamura who studies the Aharonov effect, which is very, in a sense, similar to this.
More questions? Oh, okay. Thanks, Peter, again.